In this unit, we discussed exponentials and logarithmic functions. In subunit 5.1, the objective was to be able to graph and identify transformations of both exponentials and logarithmic functions, as well as natural exponents and natural log functions. Our essential questions include the relationship between exponentials and log functions, as well as the relationship between natural exponential and natural log functions. Exponential and logarithmic functions are inverses of one another. They undo each other in the same way that division undoes multiplication, or that addition undoes subtraction, or that taking the third root, the cube root, inverses something being cubed. Exponentials are of the form f of x equals a times b to the x, where a is the initial value, b is the base, x is the input, or our domain, and f of x is our output or our range. The graph you can see has two lines, red and blue. The blue line, as you move to the right, goes closer and closer to 0. In other words, it decays, meaning that its base value has to be a fraction. However, the red function seems to grow as we move to the right, and therefore it's called exponential growth with a base bigger than 1. You can see the blue function has a base of 1/2, and the red function has a base of 2. The domain for both is all real numbers, and the range is only y is greater than 0. In other words, there are no negative y values. The x-intercept does not exist because there's a horizontal asymptote at y equals 0, and the y-intercept is at 0a. In this case of the red and the blue function, the a value is 1. Therefore, the intercept is at 0, 1. Logarithmic functions look like the form f of x equals a log base b of x. So in other words, the log, which is the inverse, is pronounced, you would say it as a log with a base b of x. The graph looks like a sideways version of those exponentials off to the left. And just for clarity's sake, I'm going to put up another graph that would show you the exponential growth inverse as well as the exponential decay inverse. The domain is only x is greater than 0. The y is all real numbers. Notice that when we talked about inverses back in Unit 1, our x and y's flipped when we were talking about inverses. So for our domain of an exponential, it was all real numbers, but for our range of logarithmics, it's all real numbers. The x-intercept is now a0, and the y-intercept does not exist because there's a vertical asymptote. The natural exponent is exactly the same as the other exponential we saw on the slide before. However, its base is the number e. E is approximately 2.71828. There is a day that celebrates E. It is February 7th. However, it's not nearly as popular as Pi Day on March 14th. The graph looks very similar to our exponential. Again, it is going to cross at 0, 1 unless we have an initial value in front of the E. Our domain is all real numbers. Our range is y is greater than 0. Our x-intercept, again, does not exist, and our y-intercept, for the most part, is at 0, 1. The natural log is the inverse of the natural exponential function. It is the log with a base of e, so it is the equivalent to log base e of x. However, we just use ln of x, natural log. The graph for the natural log of x, again, looks very similar to our log functions, where our domain is x is greater than 0, our range is all real numbers, our x-intercept now is 1, 0, and our y-intercept again does not exist because we have a vertical asymptote at x equals 0. So let's go ahead and take a look at these functions. We'll describe the transformations of each, we'll plot the graphs of them, and talk about their domain and their range. So for this function on the left-hand side, we have -3 to the x plus 2 plus 1. Let's think back to our transformations. The plus 1 on the outside is going to move the graph in what direction? If you're thinking up, you are correct. What about the plus 2 that's in the exponent? That's going to be the opposite of what you think. It's going to move it left 2. And then we've got that negative out in front, which is going to cause it to reflect or flip over the x-axis. So our graph should have intercepted at 0, 1. However, it moved to the left 2 and up 1. So if I were to plug in the value of 0 as my input, I would get negative 3 to the 0 plus 2 plus 1. That would cause me to have my x-intercept be down at 0, negative 8, because I'm going to have negative 3 squared, negative 9, plus 1. So if you can look down on that y-intercept, you can see that there would be a y-intercept at 0, negative 8. Our x-intercept is at negative 2, 0. Again, our domain is all real numbers, but our range is y is less than 1. Now, traditionally, our range was y is greater than 0. However, when we flipped over the x-axis, our range changed to y being less than 0. And then when we moved up, our range transitioned again to become smaller than 1. On the right-hand side, we have a logarithmic equation. We've got two things going on here. We've got that 2 out in front, which is going to cause a vertical stretch by 2, and the negative 3 on the outside is going to force it to move down 3. This is what our graph is going to look like. Again, our domain is going to be x is greater than 0. Our range is going to be all real numbers. Our x-intercept does not exist, and our y-intercept does not exist either. For the natural exponent, we have e to the x minus 3. That's going to cause us to move right 3. So it went from having a y-intercept at 0, 1 to us having a y-intercept at e to the negative 3, which happens to be a very small number. Our domain is all real numbers. Our range, again, is y is greater than 0. Our x-intercept does not exist, and our y-intercept, like I said, was 0, 0.05, a very small number. For the natural log function to our right, we only have one thing happening to it with that 1/2 out in front. It's going to cause it to vertically stretch by 1/2. Here's what our graph is going to turn out looking like if we were to plot it in y equals. Our domain is x is greater than 0. Our range is all real numbers. Our x-intercept is at 1, 0, and our y-intercept does not exist. So we're going to try and match each of the functions with its corresponding graph below, and we'll kind of talk through the transformations that are occurring, plug in some points in our heads to see if we can find the matching graph. In number 1, we have f of x equals 2 to the x. There's no transformations happening to it. It has a base of 2, an input of x, and an output of y. There is no a or initial value, so we know that if I were to plug in 0, 2 to the 0 is going to be 1. Therefore, my y-intercept is going to be at the point 0, 1. So I'm looking for a graph that has a point 0, 1. Using process of elimination, I'm able to conclude that that is, in fact, graph B. In number 2, it is the mirror image of graph 1. With that negative out in front, we're going to cause our graph to flip over the x-axis, meaning that the correct graph would, in fact, be A. In number 3, we now have an initial value of 4. We also have a 2 to the x function again. So if I were to plug in 0, I would get 2 to the 0, which is 1. 4 times 1 is 4. So I'm going to have an initial value, or y-intercept, at 0, 4, leaving me with graph D. In number 4, I have a 1/2 out in front, meaning I'm going to vertically shrink by a factor of 1/2. If I were to plug in 0 into that function, I would get 2 to the 0, which is 1. 1/2 times 1 is 1/2. So my y-intercept would be at 0, 1/2. My corresponding graph would be graph F. 5 is the mirror image of 4, so I'm looking for a graph that's going to intercept the y-axis at 0, negative 1/2, which has to be C, leaving me with the final plot of number 6, negative 4 times 2 to the x, having to be E. In subunit 5.2, our objective was to be able to convert between log and exponential functions and solve multi-step problems. The essential question is how to convert between logarithmic and exponential functions, and how we can use property of inverses to solve multi-step problems. To convert between logarithmic and exponential functions, we need to remember which value is in the place of what letter. So here they've color coordinated it nicely for us. We've got y equals b to the x, becoming x equals log b to the y. So if I were to convert log 2 of 8 equals x, I'm going to get 2 to the x equals 8. In that way, I'm kind of making a counterclockwise circle. 2 to the x equals 8, I'm able to solve because I know that 2 cubed equals 8, and thus x equals 3. For this next one, 32 equals b to the negative 5. I can correspond that to my y value being 32, my base being b, and my x being negative 5. Plugging that into the way it should look for a logarithmic equation, I get log with base b of 32 equals negative 5. In the third one down, I have the natural log of 5 equals x. The base of the natural log is e. Therefore, if I wanted to convert that to an exponential, I would have e to the x equals 5. In the top right, I have log base 10 of 0.01 equals negative 2. I think it's important to note here that writing the word log with base 10 isn't necessary. If you just put log, it's assumed that the base is 10. So the only time you need to put a number in that subscript is if it's not a base 10. So log base 10 or log are equivalent statements. Now, if I wanted to convert this to an exponential, I'm going to have 10 to the negative 2 equals 0.01. 3 to the x equals 81. To convert that to a logarithmic function, I'm going to get log base 3 of 81 equals x. And lastly, e to the x equals 72 is going to become log base e of 72 equals x. But we know that log with base e is really a natural log, so we can just substitute and write natural log of 72 equals x. It's important to note the properties of logarithmic functions, as these will be extremely helpful in solving the equations. So for the product rule, we have that if you have log of ab, you can split it up into log a plus log b. The same is true in the opposite direction. If you have two numbers being added together and they're both logarithmic functions, you can combine them so long as their bases are the same. The quotient rule tells us that if I have two numbers that are divided by one another, I can split them up into two logarithmic equations that are subtracted from each other. The same is true if I had the opposite. If I have two numbers with the same base being subtracted from each other, I can combine them into one division statement. The equality rule says that if log base b of m is equal to log base b of n, then m and n must be equal. The power rule states that if I have a logarithmic function of a to the b power, I can take that power and put it in the front and call it b times log of a. The same is true if I were to have the opposite direction. And lastly, the change of base rule tells me that if I have log base b of m, that is the same statement as taking the log of m over the log of b. So in other words, when your calculator will not calculate log base 7 of 5, you can plug in log 5 over log 7, and therefore you'll be able to calculate it.
So in talking about solving, on the top right, or on the top left, we need to first add 3 to both sides, so that we have 2e to the 4x minus 9 equals 112. We then need to get rid of the 2 by dividing by 2, and then we have to get rid of that exponential, and in this case our base is the natural exponent, so we need to convert it to a natural log. So I'm going to do my swirl from that e around the equal sign and back to the 4x minus 9. So I'm going to have ln natural log of 56 equals 4x minus 9. I'm going to add 9 to both sides and then divide by 4. In the middle example, I first need to subtract 9 on both sides and then divide by 3 on both sides. And lastly, I need to eliminate that logarithm by converting it to an exponential. I'm going to start at the base. I'm going to swirl around the equal sign and back to the x to get x equals 1024. And on the right-hand side, I need to first get rid of that 9 by dividing both sides by 9. I then need to eliminate that natural log by doing the natural exponent. So I'm going to swirl from that e base around the 3 and then equals to x minus 2. I'm going to add 2 on both sides and get 22.085.
In subunit 5.3, we are going to learn how to calculate the inverse of exponentials as well as logarithmic functions. In order to do that, we need to remember our 4 steps for solving inverses. So, step 1 is to replace f of x with y. In step 2, we switch x and y. Then we solve the multi-step equation for y, and then we replace it with f inverse of x. So to walk through this example here, in step 1, I'm going to change that f of x to a y. Then I'm going to switch my x's and my y's. Now, in step 3, our goal is to get y by itself. It's currently having the logarithmic function attached to it. So in order to get rid of that, we need to employ the inverse of the logarithmic function, which is the exponential. So we're going to convert it to an exponential of 5 to the x equals 2y minus 1. We're then going to add 1 on both sides and divide by 2. And in the last step, we'll replace y with f inverse of x. To calculate the inverse of the leftmost function, first I need to replace f of x with y. Then I'll need to switch x and y. And then I need to get rid of the natural log, so I'm going to convert it to a natural exponential by taking either the natural exponential on both sides or simply by converting it so that I get the statement e to the x equals y minus 3. I'll then add 3 on both sides, and lastly, I'll replace y with f inverse of x. K of x equals 2 to the x. Step 1 is to replace it with y. Step 2 is to replace or switch x and y. Step 3, I'm going to convert it to a logarithmic function with log base 2 of x equal to y. And then in one final step, I'm going to implement the change of base formula because my graph on my calculator will not graph log base 2 of x. And therefore, I'm going to convert it to log x over log 2. That I can put in my calculator so that I can see the graph if necessary. For this next leftmost example, again, step 1 is going to be to replace our L of x with y, and then switch our x and y's. Now I need to subtract 7 and divide by 6. That's those first 2 lines. I'm then going to convert it to an exponential with 5 as my base, x minus 7 over 6 as my input now, and then I'm left with negative 4y. To isolate y, I'm going to divide by negative 4. And lastly, I'll replace it with L inverse of x. For m of x equals 5 times 7 to the 8 minus x, first I need to replace it with y. I then need to switch x and y's. I need to get rid of that 5 times 7, so I'm going to divide by 5 first. I'm then going to convert it to an exponential function, a logarithmic function from an exponential function. I'm going to subtract 8, multiply by negative 1, and then I'm just going to mess around with it until I get it to a form that I like. So negative log base 7 of x minus x over 5 is the same statement as the negative out in front, log base 7 of x minus log base 7 of 5. I can then convert that using change of base if I were to so choose. I can plug those in my calculator and simplify as necessary to get my final answer of negative log x over log 7 plus 8.82. In our last subunit for this chapter, we were able to answer real-world problems using logarithmic and exponential functions, and we're going to talk about some applications and types of problems they can help us solve. So the first application is interest. We can have simple interest, compound interest, or continuously compounded interest. If I have simple interest, I have A, which is the amount that I have after time, is equal to P, the initial amount, times 1 plus R, my rate, raised to the power of my time. If I were to compound interest, the keywords that you're going to hear in the problem are weekly, daily, annually, bi-weekly, semi-annually, quarterly, monthly, bi-monthly, etc. All of those values are similar or in some way relate to the variable n, which is the number of times it is compounded within 1 year. So if I compound something weekly, my n value is 52 because there are 52 weeks in a year. If I compound it annually, I'm only doing it once a year, and therefore my n value is 1. If I do it bi-weekly, that means I'm doing it every other week. If there are 52 weeks in the year, that means I'm compounding it 26 times, so my n is 26. Quarterly, that's 4 times a year, so my n is 4. Semi-annually, n is 2. Monthly, there are 12 months, so n is 12, etc. For continuously compounded, the keyword will be continuously, and that's going to substitute E in place of R1 plus R. Notice that it's also raised to the power of R times T. Oftentimes, this function is nicknamed PERT. So in 1815, the US government took out a loan of $450,000 from the richest person alive at the time. At an interest rate of 6%, how much money does the government owe back to said person's descendants if the interest rate is compounded yearly, is just simple interest, it's compounded continuously, or it's compounded quarterly? Well, first we need to identify what our initial value is. Our initial value is 450,000. That's our P. Our rate is 6%, and we need to make sure that we write our rate as a decimal. So 6% as a decimal is 0.06. And then our time is from 1815 to the present, which is 2018. That's a difference of 203 years. So in simple interest, I'm going to plug it in. A equals 450,000 times 1 plus 6% raised to the power of 203. That's going to give me that the government owes $61.7 million. If it were compounded yearly, that means my n is 1. Plugging that into my equation, you'll notice that it's the same equation as my simple interest. Therefore, again, the government will owe $61.7 million. If it's compounded quarterly, our n is 4, and therefore we have this equation, which brings us out to $80.1 billion. And if it were compounded continuously, we have to use our friend PERT, and we would get $87.6 billion owed to the descendants of the richest person alive in 1815. Another application of exponential functions is population growth or population decay. Now, oftentimes there are environmental factors that are going to limit the way that this equation looks in real life. However, in theory, it can follow an exponential function that is either simple interest or continuous growth. So, a technician to the microbiologist Louis Pasteur noticed that a certain culture of bacteria in milk doubles every hour. The initial population of bacteria was 2,000. Write an equation to model the amount of bacteria in T hours. Find the number of bacteria present after 10 and a time when the number of bacteria is 32,000. So, because it is not growing continuously, it says that it's doubling every hour. That means that its rate of growth is 100%. So initially, there were 2,000 bacteria. Our rate is 100%. Then our function would make sense to be A equals P, or 2,000, times 2 to the raised to the power of T. If that's the case, we need to find the total number of bacteria present after 10 hours, and therefore you have 2.048 million bacteria. In part B, we are given A as 32,000. We already know P and R, but we do not know T. So we have to solve for T. In order to do that, we have 32,000 equals 2,000 times 2 raised to the power of T. We're going to divide by 2,000, so we have 16 equals 2 to the T, and we can solve for t being equal to 4 hours. Our last application is radioactive decay. So when radioactive elements begin to decay, we measure their rate based on their half-life, which is the time it takes for the sample to become half of its original value. The equation is similar to our other equations because over time our rate is decreasing by 50%. So we have our initial amount, A naught, times 1/2 to the T over H, where H is our half-life. So the half-life of zinc 71 is 2.4 minutes. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes? So setting up our equation, we have an initial amount of 100, a half-life of 2.4, and a time of 7.2. Plugging all of those into our equation, we then get that the amount after time would be 12.5 grams. Now, if I wanted to work that out in my head, I would say that after 2.4 minutes, we would have 50 grams. After another 2.4 minutes, so a total of 4.8 minutes, we would have 25 grams. And after another 2.4 minutes, which brings us to our 7.2, we would have 12.5 grams remaining.
So in our leftmost example of solving, I first need to get rid of that positive 2. So I'm going to have 3 to the x minus 5 equals 81. Now, at this point, there are two different ways I could solve it. I could simply eliminate the exponential and convert it to a log, or I recognize 81 as being the same thing as 3 to the 4th. So I can say that 3 to the x minus 5 is the same thing as 3 to the 4th. Because both sides have a base of 3, I can eliminate it and solve simply the exponents to get x equals 9. The same is true in my middle example. I can reduce 9 and 27. 9 is the same thing as 3 squared. 27 is 3 cubed. So solving just the exponents, I get 4x minus 10 equals 3. I'm going to add 10 on both sides and then divide by 4. Now, in the rightmost example, there's no base that goes into 8 and also into 205. So I have to solve it by converting from an exponential to a logarithm. So I'm going to start at that base of 8. I'm going to swirl around the equal sign and back to the 4x plus 1. I'm then going to subtract 1 on both sides, and then I'm going to divide by 4 to get an x value of 0.3899.